Yeah, hello. Welcome to this Discotech 2020 tutorial on the probabilistic model checker Storm. This is a joint tutorial with Christian Dehnert, Sebastian Jumas, Joost Pieter Katoen, the person that you are currently hearing speaking, Tim Quatman, and Matthias Volk. And Matthias will actually do the second and the third part of this tutorial. I will be your speaker of the first part of this tutorial. Okay, so what are we planning in this tutorial? In the first 20 minutes, I will give you a kind of bird's eye view about what is the probabilistic model checker Storm. Then in the second part of this tutorial, we're going to focus on how to use Storm, so how you can apply Storm to real examples from distributed computing. And part 3, in the third block, we're going to talk about the advanced features of Storm, for instance, the how to use the Python interface to use the several components of Storm if you want to build, let's say, something on top of Storm. Okay, so let's start. The focus of today is randomization. So randomization is pivotal in randomized distributed algorithms and in, let's say, ordinary randomized algorithms. And the idea is that we flip a coin, like depicted in the picture. Sometimes this coin may be biased, so it may be the case that we have heads with a certain probability P and tails with a probability Q, where in this example, of course, Q equals 1 minus P. And this randomization is used in distributed computing, for instance, to break the symmetry in a distributed algorithm. And in randomized algorithms, and think about quicksort algorithm, if you want to select the pivot element to partition your input array in, let's say, the part that is smaller than the pivot element and the part that is larger than the pivot element, there are several strategies to pick the pivot element, and one strategy is to take just a uniform distribution over all elements in the array. And this has the advantage that the expected computation time of your procedure then becomes n log n, which equals the average time complexity. But by randomization, you basically rule out the possibility to get an input which is worst case for the selection of the pivot. Okay, so let's look in particular in the context of Discotech to distributed systems and distributed algorithms. And I'd like to give you two examples that are quite elementary. So the first example is what is called the consensus problem. So we have a distributed system. The distributed system may be faulty in the sense that, for instance, a process or a processor, a node in the system may fail. Messages may be lost. These kind of phenomena can occur. And the idea is that the distributed processes need to agree on a certain value, right? So one possible example of such an agreement is that they need to agree on selecting a leader. So that's a typical example of agreement. So they all have a certain initial value, and after some processing an algorithm, they have to agree on that value. And the idea that in particular the correct processes, the correct nodes have to agree. And there is the famous Fisher-Lynch-Patterson impossibility result that says if we have an asynchronous setting, so we have an algorithm in which the processes communicate in an asynchronous way, and only one process even may crash, so it's a very limited, let's say, fault-tolerant scenario, then there is no distributed algorithm that solves the consensus problem. So this impossibility result has given rise to, let's say, several techniques to circumvent this, to avoid this impossibility. And one way to avoid it is to use randomization. And there are several randomized consensus algorithms, but one of the first was by Ben Orr in the early 80s. And he says, well, if a process can not only decide on its internal state, the messages that it can receive, but also has access to, let's say, some randomization, like flipping a coin, then consensus in an asynchronous setting, so the setting of the impossibility result, can be almost surely achieved, and almost surely means that this happens with probability 1. Yeah, so there are scenarios in which perhaps there will be no consensus, but those scenarios will happen with probability 0. So with probability 1, almost surely we will reach a consensus in an asynchronous distributed setting if you have this randomization. Now, a similar phenomenon occurs in the notion of self-stabilization. So self-stabilization, to put it short, is the ability of a distributed system to autonomously recover from transient faults. So a process may, for instance, fail, and then after a certain amount of time, after a certain number of computational steps, the system in some sense recovers and gets into a stable configuration again. So you may think about a distributed system where you have several tokens. The stable situation is that there is a single token. But because of transient failures, it may be the case that temporarily there are several tokens in the system, and then a self-stabilizing algorithm will recover from that situation by some algorithmic means, such that in the end we again end up in a scenario where there is only a single token. Now, there is this result by Dijkstra in the 70s that says that self-stabilization in networks where all the nodes are anonymous, so you're not supposed to use the identities. You're not supposed to distinguish, let's say, process number 3 from process number 7 because all nodes are anonymous. This is impossible. So similar to the Fisher, Lynch, and Peterson result, this is an impossibility result. And again, you can solve this because you can break the symmetry by using randomization. And this was proposed by Ted Herman in the early 80s. So just to give an impression about this algorithm, we have a ring, and suppose we have an odd number of processes from 0 to n. Every process has a Boolean variable, and the only access you have is the access to your neighbor. It's a unidirectional ring, so you only have access, for instance, to the values of your left neighbor. And now what happens is the following. So process I compares its value to the value of its left neighbor. This is happening here. And it sets its own variable to 0 with a certain probability, let's say p, and it sets it to 1 with probability 1 minus p. If your value differs from the value of your left neighbor, then you copy the value of your left neighbor. And now what you can see is that you can say, for instance, that a process possesses a token if it has the same value as its left neighbor. And suppose that we're interested in a stable situation where the system has only a single token. So then we would like to have only one process whose left neighbor has the same value. So the typical metric to measure the performance of this algorithm is to consider the expected convergence time. So what's the expected number of computational steps that the algorithm, the distributed system, needs to end up in a stable situation? Now, in Herman's protocol, this of course depends on the probability, the bias of the coin. So just to give you a flavor, what you can do with, let's say, model checking, is you can look at rings of different sizes. So here what you see is that we get from rings from a very small size, let's say 3, up to, I think, a ring size 21. And on the x-axis, you see the bias of the random coin. And on the y-axis, you see the expected convergence, or sometimes called the expected recovery time. So the number of steps until reaching stabilization. And by means of model checking, what we see is that if the ring, let's say, has a certain size, for instance, the size, let's say this size over here, right? then we see that we have for two different probabilities, the expected recovery time is minimum. So we get two, let's say, symmetric probabilities for which this is minimal. For small ring size, is not the case. And these results are obtained in a fully automated manner using probabilistic model checking. Now, probabilistic model checking has several other applications. One of them is on the left upright row, a robot moving through a room where it moves probabilistically and it needs to reach, let's say, a certain location, like here. In reliability engineering, it's used. Randomization, of course, is used in probabilistic programs or randomized algorithms, where every now and then you flip a coin, like here. In aerospace systems like satellites, randomization is used because you have errors that can happen with a certain probability, and you like to know what is the probability of the mission of a certain satellite given certain error behaviors. Many security mechanisms are randomized. And in systems biology, the reaction of, for instance, enzymes or molecules is typically a continuous stochastic process. So what Storm is doing is actually, it belongs to the field of what is called probabilistic model checkers. And probabilistic model checking is believed by at least a few people to be an important direction, because it allows you to check not only correctness, like absence of deadlocks, but it also allows you to compute quantitative information about your system, like performance measures, like in my distributed system, the expected number of steps until stabilization. Also in this paper on the birth of model checking by Ed Clark, he states that probabilistic model checking is one of the main challenges for the future. So if you look at probabilistic model checkers that are around, then actually the first thing that we have to determine is what are the kind of models that we are going to consider. And these models are categorized in terms of discrete models and continuous time models. And the way in which these models behave, so either they can be fully deterministic, which means there is no non-determinism, and then you end up with models like Markov chains and continuous time versions of it. There are models that combine non-determinism with probabilities, and then you end up in models like Markov decision processes, very popular in planning and also in actually to model randomized distributed algorithms, and continuous time versions of it, and then we talk about CTMDPs. And then there are models that are also compositional, that allows you to describe your system in a very modular way. And Segala's probabilistic automata are actually very similar to Markov decision processes, and a similar connection you have between continuous time Markov decision processes and Markov automata. Now, there are several other models around. There are model checkers that support, for instance, probabilistic timed automata, vector addition systems, so Petri nets, push-down automata, stochastic games, and so forth. If you look at the kind of properties supported by model checking, then again, we distinguish between discrete and continuous. Let's only focus to discrete in this setting. And then there are logics. So there are logic like, for instance, versions of computation tree logic. And you can also specify your property by means of what I call a monitor. It could be an automaton that you put in parallel to your entire system. That is a kind of observer. And this observes the possible behaviors of your system and either accepts them or rejects them. This can be done, for instance, for safety properties. You can also do this for linear temporal logic. And for probabilities, then, if you have your system like a randomized distributed algorithm modeled by a Markov decision process, you express your property like an LTL, and then you're interested in what's the maximal or the minimal probability to satisfy your property. If your model has no non-determinism, then you're interested in what is the probability to satisfy this property. Now, there are several other measures like conditional probabilities. You can think about multiple objectives where you try to find some kind of Pareto front between, on the one hand side, using energy, and on the other hand side, achieving your target in your algorithm, quantiles, rewards, and so forth. And the core problem that model checkers solve is to compute reachability probabilities, and in the continuous case, timed reachability probabilities. Okay, this is not the purpose of this tutorial to talk about the algorithms that solve these things. There are several algorithms to compute such reachability probabilities very efficiently, and those are the algorithms that are exploited by model checkers such as Storm. Okay, so there are several model checkers around, and what are the three main characteristics of Storm? It's a fast tool, and often the fastest. So since 2019, there is a competition between what are called quantitative model checkers. Let's call them probabilistic model checkers. And also this year, but also in 2019, this is a statement from the evaluation report of this year. Overall, Storm dominates the competition. So for many cases, we are the fastest. The second characteristic is that Storm supports several input languages. So there is Yanni, there is a language for the model checker Prism that has been established as a kind of default standard over the years. That's of course supported. We support Petri nets, we support dynamic fault trees, and guarded command language programs in PGCL. And the third important asset of Storm is that it is modular. That means it is set up in a modular way such that on the one hand side you can easily extend or exchange solvers and symbolic engines in the model checker. So that means if you're interested in using, for instance, another BDD package, then it's easy to plug in a new BDD package. If you're interested in using another solver, you can plug in another solver. And the second important consequence of the modularity is that it enables rapid prototyping. We provide a Python API via which you can access the several modules inside Storm, and that is then can be used to build your own, let's say, tool on top and reusing the components that have been implemented in Storm. So let's go through these three assets one by one. So Storm is fast. This is a picture that on the x-axis gives you the number of instances out of a certain selection that can be solved. And the y-axis tells you the amount of time, log scale, in seconds that these model checkers need to solve these instances. The most popular model checker that you probably are aware of is the model checker Prism, which is the green curve. Storm is the red curve, and it's obviously that the lower the curve, the faster you can solve instances. Input languages. There is Yanni, the intermediate language that is used for many probabilistic model checkers. So nowadays, almost all probabilistic model checkers support this. So it provides a uniform platform to describe your models, and then you can use as backend any probabilistic model checker you're interested in. We support generalized stochastic Petri nets, which is a very prominent model in performance and dependability analysis, and which also can be used to, for instance, model distributed systems. And we support a notion which is called dynamic fault trees, which is a prominent model in reliability engineering. So these are native input languages. And that means that, for instance, there are tailored state space generation technique, tailored reduction techniques for these specific input languages. Storm is modular. That means it supports actually various solvers. And here you see the various solvers to solve, for instance, linear equation systems, which are used to compute reachability probabilities. Linear inequations or linear equation systems that are used for Markov decision processes, where it supports, for instance, CUDD, which is an empty BDD package, but also Sylvan, which supports, for instance, multi-core BDD operations. Good. For the rest, we solve sometimes stochastic games, symbolic stochastic games, we every now and then need to solve mixed integer linear programs, and there we have tools like Gurobi that supports that. And we use satisfiability modular theory checkers like Z3, and sometimes we use nonlinear arithmetic, and there for that purpose we use SMT-lib. This is a plot or an overview from the competition overview of 2020. And what you see is by Storm is actually that Storm supports many input languages, as we have seen before. That is the first couple of columns. Then we have those different models like Markov chains, continuous time Markov chains, Markov decision processes, Markov automata, and probabilistic timed automata. And what you see in the last row is that Storm actually supports many of these features. What kind of features do we have? Storm has an engine to do exact model checking, so using exact arithmetic. We have also techniques that are sound in the sense that if you use floating points and you use typical techniques like value iteration, the results can be guaranteed to be correct. We have techniques to reduce models like symbolic biosimulation minimization and game-based abstraction. We support multi-objective model checking, in particular for models like Markov decision processes, but also for Markov automata, so the continuous time version of MDPs. What is an important feature of Storm is that it provides you also with counterexamples. So in case a certain property is violated, it can provide you a counterexample. For instance, in the modeling language Prism, it will even give you a counterexample in the language itself. We support parametric model checking. So if you remember Hermann's protocol in the beginning, then there was this bias P. You can use that bias as parameter P, and you can synthesize the values for P for which, for instance, the expected convergence time is minimal. Dynamic fault trees I mentioned before. You can synthesize schedulers for Markov decision processes that do not only have one choice but are permissive. That means it gives you a menu of choices in states, and we provide quantiles. The internals, there is a passing phase, which is the topmost part. Then we go to the model building. We have several techniques to minimize. And then there are, on the left-hand side, miscellaneous techniques and verification techniques. And as output, we provide counterexamples, schedulers, probabilities, rewards, and so forth. So the take-home messages of the first 20 minutes is that Storm is a modular probabilistic model checker. It features multiple input languages, and it's fast. And there is the link in where you can find more and where you can download the tool. It's open source. There's documentation there. There are several papers that describe Storm, so you can use that if you want to use Storm. Okay, in the second part, Matthias is going to explain how to use Storm, and in the third part, we're going to focus on the advanced features of Storm.